Good afternoon, everyone. My name is Carl Frey. I'm the director of the Future of Work program here at Oxford Martin School. And it's a great pleasure to have the opportunity to introduce Lingfei Wu, whose work I've admired for a long time. In fact, his paper that came out in Nature a couple of years ago on the structure of teams and its impact on scientific discovery has been fundamental to my own understanding of this topic, and so it's particularly gratifying for me to have the opportunity to host him here at Oxford Martin School. Ling is assistant professor of information science at the University of Pittsburgh. He's worked on big data, complexity science for a long time. Most of his work focuses on the science of science, a field that he has prominently shaped over the past few years. Reading out all his publications and titles would be a little bit like, listing all the majors Tiger Woods have won, so I'll spare you that. And just say that Ling is going to talk for around 45 minutes. We will then have a conversation around 15 minutes. This event is being filmed, so if you don't want to appear, then please do not ask a question, but please do ask questions because we want to have a stimulating conversation. So with that said, thank you very much, Ling, for being here, and looking forward to your talk.
Thank you, Carl. Yeah. It's such a great honor in this building with great tradition and conventions and all these startup vibe. So today I'm going to share a little bit about my research findings in the rising community of science, and in particular the collaboration problems. One thing that I think we all face more or less at some stage of our academic life is the collaboration with home problem, right? So this is we all know that not everyone has the same visibility in science. Some people have more, and you usually have more when you are more senior. So one of the sociologists in 1960s, Merton, pointing out this phenomenon as Matthew's effect, in the way if you are a red dot, already established, you typically get more citations, right? People remember you for everything that with your name. Right? And if you are a blue dot, the junior people, you are less likely to be remembered because that's Merton explained is a very selective memory because people cannot remember so many things, so they tend to assign a few names to a lot of discoveries. And this phenomenon, of course, is rediscovery and better this time quantified by Barbashi and his colleague Albert, called preferential attachment. Now this brings us to the problem of collaboration while all these studies about citation and impact. Because this study built on the assumption that every scientist works individually, right? So even in the individual scientist system, you already have this problem. We cannot remember everyone. We have to remember a few of them. Now this becomes even more challenge when people start to collaborate, right? Because if now you have, what if I'm a blue dot and I'm collaborating with the red dot, and who they will remember? We have a bad feeling coming up already, right? But there's still lack of empirical foundation and evidence to this problem. So let's look at more empirical evidence that around this. This is what today's talk is going to be about. And I start to worry this more because now, recent days, I have a very realistic worry that what if one day my team got a Nobel Prize, right? Like my work on Nobel Prize, it's very realistic. And who will go to take the prize? I ask that question and I look at the empirical data in this to get myself a little bit sense and get prepared for that. In the past 100 years, you look at the physics, chemistry, and medicine, there's almost the same pattern. On one hand, you have more and more people need to involve into this groundbreaking work. You know, of course, send someone to the moon, discover dark matters, gravity, human genome. These are huge projects, huge projects. But our award system is behind. We haven't defined the award system, a system that everyone in the team will get the prize. So unsurprisingly, the number of people in the team that go to take the Nobel Prize remains very stable. So we see this huge gap here, right? The gap of forgotten people, right? People who do things that eventually earn Nobel Prize, but may or may not be remembered. So this brings us to the question of who does work in the teams, and do they eventually get recognized? Right? This becomes such a fundamental problem in today's reward system in science for it to be functional. But it's very hard, because when you look at a paper, how do you know who write which part? It's almost impossible, because with the moment when you see this paper, it's typically already done. Right? And now we use a very interesting technique to look at the table, to look at the paper in a very specific way. And before we proceed to that, I'd like to have a quick question. How many of you have heard of latex? Can you raise your hands? Thank you. You can put your hands down now, nerds. Thank you. So same as me, if you don't raise your hands at this point, you have a lecturer's life, never called a nerd before. I don't have that. I spent a lot of years writing things, and actually until last week, I still work on my overleaf. Nowadays in academia, especially in economics, in mathematics, where there's a strength emphasized in equations, we use latex a lot. Now, there's a beautiful thing about latex is, if you, wow, this is really a small dot. I hope you can see that. If you look at this PDF, you don't see nothing. It's just like an average, a mediocre half, right? But if you look at the source code of latex, there are different ways to write this. Isn't that interesting? This is like the mediocre average way to write this. And sometimes people become creative. They want to lead a little bit trajectory, digital trajectory in the world. So they try to have their own styles. And this allows us to identify personalized latex macro, right? Meaning that you actually can build a history of this thing. If you look at the paper, this two-person paper, Hooper and Linder on arXiv, because when people upload to arXiv, the largest website on preprint in computer science and statistics, they usually ask you to upload a LaTeX source file. So you can collect the source file and map out the entire history of this person's LaTeX files and extract every single unique macro, personalized macro in their history for one person and another person. And this way, when they build all these individual trajectories, when it comes to the particular paper that we are talking about, you already know that who is potential to contribute what, because they used this macro before. This is like a digital fingerprint in the files underlying that paper. So with that, you can calculate the total number of unique macros and the share between these two authors, and use it as a proxy of writing contributions. Are we all good with that? Okay. But of course, this gives us a beautiful, beautiful perspective of a mathematical or symbolic space people operate, right? So this shows the entire history of one person and another person. And you know, at some point, I think this project gives a lot of hope for people who study collaborative learning, because you can see how after collaborate with one person, they adopt the system and try to use the same symbol. The beautiful, by looking at this, using this technique, we look at the 1.6 million papers that associate with latex files that contributed by 2 million authors, so almost the entire archive. And from there, because we need a sufficient history for people to of macros to identify their contribution, so we didn't get everyone, but we get a large portion, 500,000 authors and more than 500,000 papers they contribute. Okay. So this is a great success with a new kind of data, but we cannot trust it yet because it hasn't been verified. Next, we are going to verify that through different complementary methods. The first way, of course, is to compare what we observe from people against what people say about themselves, right? So these are like self-reported contribution statements nowadays required by PNAS, Nature Science, PLOS One, and others. And we can collect nearly 500 statements from these top journals. And in each case, we know on left hand, we know what they actually do. On the right hand, we know what they say they do, right? And we can compare that. And this gives a very high precision of the writing contribution. So when people say they write the article, they actually write the article. Right? This is good news. Scientists are at large trustable. The second is we compare that with 14 individual cases, right? The ideal case is overleaf. Everyone's overleaf record. So we negotiate with overleaf. And we basically write emails, can you just give us that data? And of course, the answer is no, because they have privacy concerns. There are interesting story and drama out there. We can find another time to share. So as an alternative, we go to our friends. So this is the moment when your friend becomes useful. We say, can you just give us your data? And to trust us, the 14 friends, not all the friends, unfortunately, agreed. So these 14 friends pass us their individual history of edits. So this is like actual, like minutes by minute, second by second data on actual writing. And we compare that with the data set we developed. It's highly correlated in terms of ranking of all the contributions. Things started becoming more interesting when you verify it with some graphic things like you plot the contribution. Now we can start to trust this contribution more and more against all the authors. And you find that it's almost decline. This is consistent to what we perceive as what we do in the academia. Usually the first author take the most of credit and do most of work. And as you move to the later part of the author list, they become to do less. So this is consistent. Sometimes things can be different across disciplines. In economics, people still practice a lot of alphabetic orders, so they randomize their orders. And I try to write this because my family name is Wu, so every time I have to, that's why I don't do a lot of economic journals. Very fun system, right? But I'm more like from computer science. That's the system I'm familiar. I'm moving like from here to here, so life is getting better. I'm doing less in the work. And the reason of that is like computer science operates such a way, if in case you are unfamiliar with that, all the students are supplied by your fundings, and you need to get the fundings to supply them. So it's like you really run your little startup. And so lots of other mostly contribute to bring money to the table rather than do the work. And it relies on your self-consciousness of do how much work in the paper, okay, in your lab. But the bottom line is we do see these different discipline culture. And here's my favorite, across all disciplines, you see this division of labor. Like we talk about division of labor like for hundreds of years in economics, right? It's like the fundamental way of looking at how market work. And we start to talk more about that more recently, right, in science. But this is the first time we observe that empirically in teams, how scientific teams divide work. And you look, like the beautiful thing about this latex data set is you do have a specific label of sections. You know what is introduction, who writes introduction, who writes conclusion. These are specific. This is not inferred because they have a subsection title, introduction, right? Okay, so with that, you can clearly see the division. Some people write more about introduction, conclusion, discussion, acknowledgements, right? Mostly conceptual work. Some people write more about methods, results, experiments, preliminaries. These are likely the people who rank earlier in the order, right? So this is beautiful and consistent with what we think, verified with this established long-term hypothesis of division of labor. Now with that, without bringing you to more technical details, I'd like to jump to, I think at this moment we all know, like we do have a good data about what people do in teams, but we don't have a measure of what people get from teams, right? And this is built upon established algorithms. Ignore the details. This is just imagine something like PageRank. Like it calculates like a random walk mathematical model in the collaboration network and predicts the credits. So it's called a credit allocation algorithm developed by Shen and Barbas in 10 years ago, right? So this works well. Applying the algorithm, they verify that with Nobel Prize. So yes, that's my inspiration source, right? You look at Nobel Prize again and again, like you will get it, right? So they get a very nice 81% prediction of, even within the Nobel Prize winning work, who in the team will actually go to take that prize, who is considered as the person come up with the idea, major idea by the Nobel Prize nominating committee, right? So it's very high. And now now we have, finally, it's a little bit a long walk. It's about 20 minutes in my talk, but about 2 to 3 years in the real work. We finally have these two pieces, right? On one hand, we know what people do, right? You know what people do in teams. Nobel Prize work, but more than that, we have, let me remind you, we have 500,000, and more than 500,000. And we know who get the prize, right? And not just Nobel Prize, who gets what credit score they actually get that can predict the Nobel Prize. So we extremely extend these two parts of data set from Nobel Prize situation to almost covering everyone in science, right? And what we found at this point, first of all, just out of pure curiosity, we look at how what they do change with author rank, and what they get change with author rank. And it's like across all team size, what you do declines and what you get increase, right? So it's beautiful to be the moving to the to the latter part of the team, right? This is the first empirical evidence based on observational data that shows this huge gap and asymmetry in what you do and what you get, right, in science. And of course, we want a more rigorous model of regression and all that, statistical, not just descriptive. So we predict the chance you get you are the person recognized, like you are the person. We ask the question, who in the team will go to get Nobel Prize if this team actually got the work, got recognized. So it's like the maximize accredited person. So are you the maximum recognized person in the team or not, right? So it's going to be a logistic regression with the dummy variable as a predictor. And we controlled, are you actually also the person who do the most of work in the team? So person who do the most of the work as a independent variable here, top contributor. Person who actually get the most credit as the independent variable out there. So these two binary variables. While controlling these binary variables, the ideal of science is like almost nothing significant, because a perfect merit-based system in science will be strong correlation between these two, and no correlation, no significance and for anything else. But apparently our real world is deviate from that primary in the age part, right? So if you have, you're getting older, so this is congratulations. We all have hope, okay? Let's put it this way. We all have hope. As we are aging and just stay in science, don't leave, right? You get a little bit more gift from time, right? And sent by your peers, right? Okay. And last order, specifying your role in last order gives a little bit premium. Being male give you a little bit premium. Publishing high impact research, a little bit, almost no significant premium. And these two things are negative because when it shows that when you have more recent work, on average, everyone is less likely to be recognized, right? Because not just because teams are larger, team size is the most negative because when you work in larger teams, almost nobody got recognized, right? So if you look at this, you'll see this more clearly. This 2% team, you almost even split the credits. When you go to bigger, like the credit is diluted, divided and diluted, right? But even after diluted, the last guy is better than the first guy, okay? But now, so older work have better, is more merit-based, and science is getting less and less merit-based over the years because publication year is negative after you control everything else. And large team itself, of course, dilutes it. So the last figure I want to show you in this conclusive scenario is to show how these three things, age, team size, and the credit interact. You can run this, show this in different regressions, right? And then you see that as team age goes up, you usually have a bigger gap between top contributor, which is the blue line here, and top recognized order, which is the red line here. So there's always a gap with the career age, right? Now this gap becomes bigger in larger teams. Surprise, surprise, right? Because mostly large teams are led by these senior people, and eventually, no matter how much amount of work they do, they always the credit always go to them. So, and beyond this single study, I want to introduce a little bit background. I think this is the right time to bring us to the bigger picture of what's going on in science and why things matter. Okay? So this is one of the turning point in my academic career to contribute to this conversation about the creativity and collaboration problems in science. And there's an ongoing, I think it's not concluded yet, ongoing conversation about why science is getting less excited. Right? We kind of all feel that, but is it just a subjective feeling? Is it just like we are getting grumpy over time, or is it real? Is it science actually getting less excited? There are many answers, and this is the last year's Nature cover article show that there are some evidence to this, right? Although there's controversies, but there's strong suggestive evidence. So why? Why science is declining in the average innovative level of ideas? There are many explanations, but my explanation to that is it's associated to the way we organize science, right? So not many people notice another paper, but and its association with these, but it was done by Brian Woozy and Uchi and their colleagues a while ago, talking about that universal, the science are getting bigger, right? We are switching from small science to bigger science. And this was my and colleague 2019 Nature article established the linkage between these two phenomena, saying that if you have bigger teams, you are actually typically getting less likely to work on these radical fundamental ideas for many reasons, right? For communication costs, because you need to reach consensus, for the burden of money, because you need to deliver and there's no time to innovate at some cases, and for many interesting reasons. So the conclusion of here, of this this kind of collective conversation, I think it's the team has a cost in individual creativity, right? If you want to be most creative, teaming up with a lot of people may not be the best choice. But then why? Why teams fail, right? I think one explanation is team, by collaboration, it promise more brains, but actually over-promise and deliver, it go with muscles, right? So this goes with my last year collaboration with Carl Frey and lead by my PhD student, Yiling Lin, on Nature. We look at the teams in the context of global collaboration, and long story short, you see that as thing expands, it doesn't explain. Let me put it in a very offensive way. Brains, right? The brain doesn't expand. It brains with these muscles, with this technical work. So when people say we need to collaborate, so we visualize these global collaboration patterns with millions of scientists across 3,000 cities. And we color that in blue if it's less innovative, using a metrics we help develop, disruptive in metrics. And we color it in red if it's highly innovative. You see that almost a majority of this global collaboration is about deliver something. It's about execute someone's idea 50 years ago. It's less about let's get in the next exciting idea done, right? So this is what actually happens in teams. Teams give us a little bit illusion, right? Of course, it gives us a lot of other benefits, maybe emotional support, maybe the belonging things. But what's happening in reality is that it doesn't make us, all people in the teams have got the equal power to say, and to talk about our most creative idea. It's really about getting a lot of people to deliver a few people's ideas. So with that, I will conclude my talk. And this is like, with this work and ongoing work, I try to contribute to a complementary perspective of teamwork. Because people have been celebrating for a long time. We talk about how they accelerate your productivity. Collaboration make you more productive and likely to have more citation impacts. Of course, if you have more people in the team, more people talk about that work and more connected. It's unsurprisingly teamwork will have higher impact than more visibility than individual work. But really people actually recognize the cost of teams in innovation, creativity. First, we established through our previous work in 2019 and 2023 on Nature that it does hurt individual creativity. As evidence, teamwork is not as much radical and innovative as individual work. It's about delivery, it's an execution, not about idea generation. And this new work, this new ongoing stream of work, we show the second hidden dimension of teams in terms of recognition, right? Teams divide and dilute credits so that make it a black box that it's very hard to tell who does what in teams. And when they tell, they're not always favor for you, right? So through this whole stream of research, mostly delivered by my PhD student, Yiling Lin, a great student who leads the 2019 Nature paper, and my newly high potential recruit, Lulin Yang, who is the main contributor of this recognition dilution problem, and my research assistant, Jiaxin, who now the postdoc at Stanford, a great collaborator who helped come up with this idea of using archive data to see contribution and build data sets. And as you can totally understand at these points of my talk, that they are the first order do the work. I just came here and talk about that. Okay. And I'm Lingfei Wu at the University of Pittsburgh, and I welcome all these follow-up questions.
Thank you very much, Ling, for that wonderful overview. We are going to proceed to take some questions from the audience, and I may take the freedom as a moderator to inject a question from time to time. I hope that's okay. Please, when you ask a question, briefly introduce yourself and preferably ask a question of the kind with a question mark at the end of it. We can take a few, I think 2 or 3 at a time, and then feel free to respond in which order you like. So, any questions?
Hello, thank you. Felix Rietzochers from the Side Business School. I was just wondering, thinking of the first part of your talk where you're looking at the micros from LaTeX edits, how you think about the relationship between what you see when you're thinking about writing contributions and what you can see in terms of the edits people have made, and how we would more generally think of contributions to a paper. So I might, for instance, say to a co-author, oh, this is a terrible notation, I think we should do this. Could you please implement this across the paper? And then you will see the traces of their edit activity implementing that. So I'm just wondering how you think about how these two things are related.
Yeah, this is beautiful. My observation is that you already see this huge inequality in labor division and who does what and who gets what. Even we assume these people who write that are actually people who write that. And you bring this to the new, put this to the new exchange and say that, what if they don't even write that? I assume that even that exists, it will it kind of point to even stronger inequality. You're basically saying, what if there are people like didn't even contribute to the LaTeX? And I assume that they actually contribute less, even less, and likely getting more, otherwise people wouldn't listen to them. So they will amplify the story. But back to the quality of data or the limitation of the data set this point to, for fields like computer science, mathematics, statistics, I think largely it's very hard to ask someone else to do the work because this works heavily relies on equation edits. And the main body is really just about an analytical work and additional text that explains them. So I will imagine what you said wouldn't be the major concern there because it's very hard to ask people to edit the equation and text in the way they like. And you basically, if you do that, you lose all the funds in academia. So I don't believe senior people will do that all the time. But I think it raises a legit concerns and it should be more carefully tested. Even we already tested with self-report, we should probably do more interviews and see how often this happens.
I mean, I'm just coming back anecdotally,
Yes,
and this is many years ago.
Yeah.
I remember working with a senior author, this was in statistical physics, and he was terrible with LaTeX. So, you know, he would say, I think this is what we should do, and write something down on the blackboard, and I might then implement that in LaTeX. But the idea of writing something in a certain way initiated on the blackboard and not necessarily in what I was doing in kind of then translating that into LaTeX.
Yeah, this is data set covers 1991 to 2020. So I believe the portion of that people is getting very, like, it's not a huge portion.
Fair enough.
Yeah.
So William Morris from UKAEA. So I work on fusion research. One of the things which has evolved over time has been the complexity of the research topics and research fields, typically requiring very large teams in order to grasp and handle all the data and information. And that may be behind some of the trend towards disruptivity. And I was wondering whether you had found any signs of what helped disruptive papers in these complex fields? Were there any had you looked at that, were there any characteristics of the teams which lead to disruption in a field which might appear highly viscous?
Can I rephrase your question a little bit? You are saying what's the secret sauce of being disruptive, or?
I was wondering if you had found any signatures of disruptive research and publications in fields which are typically very complex and have very large teams, are intrinsically required to have very large teams. And had you seen any signatures of what constitutes disruptive behavior within large teams?
So related to this, I think a question goes a bit to Ben Jones' work about the burden of knowledge. And so does your work rhyme with that hypothesis overall? And is there anything particular to disruptions in sort of more complex fields where the burden of knowledge might be very large? I take the question.
Yeah, or my understanding is if we're already in computer science or biomedicine, and we do have a lab, and we need the lab to deliver that work or to do AI. And now you need to have a big budget, big bills, big things to even start doing that. How do we understand? How do we disrupt in these kind of scenarios? That's a very interesting question. I actually have this follow-up interaction with Ben Jones, and my point is that the burden of knowledge theory, which assumes that you need, if you have more people to take the burden, or you have longer training to take the burden, so that you can innovate, could be problematic, because if you look at the history of science, every generation of innovation, think about quantum physics, they are not by the people who knows best of the old knowledge. They are the people who are actually very ignorant of the old knowledge. So if you go to check the great GPAs of these quantum physics founding fathers, who by then in 1920s were like 20, 30 at their age, they are not the best students in the class. They know actually very not the best about the knowledge. So my observation is that when science has this paradigm shift, it's usually led by younger and more ignorant people. And therefore, I'm not sure to what extent the burden of knowledge theory holds in that the more you take, the more you can innovate. My understanding is that the more you take, the more you fix to that ideal system. And we do have more evidence coming out in my ongoing research and the review in Nature now about the age and creativity. And you see that there are two kinds of creativities. Same with age and same with the team size. Getting older and getting bigger teams, you get a certain kind of innovation, that is recombinant innovation. Because you know more, and then you can operate in a bigger space of their possible combinations, so you are better at combining things together. For example, if you have a candle, and you find the candle is not work, and now you invent the candle holder and you put a lot of candles together. That's a certain kind of innovation and will carry science forward for a while, but I would say it's definitely not a disruptive innovation, which is a light bulb. You basically redefine the candle. So back to your question, I think in computer science, in biology, biomedicine, where usually you have these large teams, this moment happened when Church Turing invented Turing machine here in UK by himself. He didn't have a big team. And when Chris Washington and Crick in 1953, also in UK, proposed the DNA structure. And you'll find that all this, even in this huge emphasis on large team and deliverable fields, the critical moment, the definitive moment of science in coming up with a new generation idea is usually by one or two people. And then later on, they need to assemble very large teams like Von Neumann in US, like Human Genome Project. You need to have very large teams to implement that. So I don't think this kind of trade-off between team size and the disruptive innovation capability and the fundamental difference between two kinds of innovations the recombinant one and the disruption one will vary across fields.
So basically what you're saying is that if the burden of knowledge was the key bottleneck, we should see older researchers rather than younger researchers pushing more the frontiers of innovation, and you're saying you're finding the opposite of that in your research. One would also suspect that productivity tools like AI or computers, the internet, tools that allow you better to sort of get to the frontier of knowledge in a field more quickly, and should have an impact if the burden of knowledge was a key bottleneck. Is there research along those lines to what degree these sort of productivity tools might help?
Yeah, it's a rising common belief that AI will take this burden of knowledge for us. And I actually do that too. Right? Nowadays, I ask ChatGPT a lot of questions and instead of Google. But it's very interesting to look at what AI specific impact science. The major way impact science is just like reduce our writing work. Now, when it comes to innovation, you will find that the most successful way AI directly innovates something, accelerate discovery in science, usually happens in recombinant innovation. For example, in proteins. So AI can come up with more, this is my limited knowledge about AI. They come up with faster with more possible combinations of protein structure and help you accelerate the search. And the writing is essentially the same thing. They come up with a better and faster combination of words to make a document. And you'll find that these two most successful fields are all about recombining. We're not sure yet how AI redefines existing idea. Basically say, hey, we probably shouldn't look at the gravity in this way. We should look at the gravity in another way. But with that said, I think there's still, I don't think it's too early to conclude that they cannot do that. But I just haven't seen the evidence how AI can challenge established knowledge the way that the human used to do that to advance science. And actually talking about the additional points, we are doing a fringe, I feel I'm selling a fringe science of my personal understanding here, is that human science advances in such a way that relate to human limitations. Because we have small brains and we can remember very few things. And every time we talk to each other, we spend a long time talking very little things. So our science has this property that we prefer the shorter expressions. We prefer the short theory that very condensed, equation that very short. And this is all adapt to our system, the human science, right? So every generation, when we talk about paradigm shift from Newton to Einstein, they basically write shorter equations with more information. Does AI do that? I don't know. Does AI like that? I don't know, because they don't have this brain limit problem. So if AI got to choose their own science, it could happen in an alternative way. They will remember everything. So I like to bring this perspective. I'll stop here, but bring this fundamental difference between human science and machine science. I think that will help us think what kind of transformation will be happening.
Other questions from the audience?
Thank you for the wonderful presentation. I have a quick question. In your research, you showed the high cost of large teams, and I'm wondering what are the implications for the current academic system where editors and the founders seem to prefer like large team science?
I don't think editor will naturally prefer large team. They usually prefer established names, but as a consequence, they bring large team. I have very little suggestions. I think, luckily, we are in Oxford Martin School, and I can see the vibe here is encourage independent thinking. I think it's important to think of the financial system especially given the recent interesting news going on in US, to support these individual scholars. Because in the end of the day, the reason why this increasing dominance of teamwork, and they are important to science, but in delivering execution, not in creativity, is basically just money talks, right? So as an assistant professor, I need grant money to hire my PhD student. And to get that grant, I need to write proposals. And which means, very unfortunately, even before I hire that person, I already decide what that person need to do. Otherwise, I won't be able to deliver my grant. I cannot get my next grant. So I suffer from this system as much as everyone else. And I wish we can have come up with better funding systems, or at least alternative funding systems that funds individual junior scholars. And that will change again.
So has there been a general shift whereby what you're describing is young people coming in and you have a professor who sort of defined the question for you already?
Yeah.
So has there been a shift towards that generally? That if you look sort of over the decades, did it used to be the case that young researchers have more autonomy than they have today? Have you seen anything on that in the data?
In my specific data, I haven't, but I believe that's the story going on with all other people's work and all these small large science.
And let me push you a little bit on the policy implications as well, because two things you mentioned: large teams, remote teams, bad for disruption. If you look at Horizon 2020, huge consortium spread across space in Europe, very large teams. It seems to me that your research does suggest that that is definitely going in the wrong direction, or am I misreading that?
I don't know about the specific case, but yeah, I mean, based on my data, I very rarely see large team do something very creative.
And why is that? So what in your view is sort of the mechanism that means that smaller teams can be more creative? Is this the consensus?
So there are two fundamental explanations. One is about communication cost. Right? So when you have a lot of people in the room, you need to arrive at consensus. It's unlikely to be the consensus. It's unlikely to be the most creative idea among all possible ideas. So that's the communication cost. The regression to mediocre when we have a lot of people. The alternative explanation is about the burden of money. Right? It's not a burden of knowledge, but burden of money, because you already take $500,000, 1 million to assemble this team. So you are at any moment you're under pressure of publish, deliver, and really reduce the mental resource to create and the risky consequence that may lead to. So we do find evidence for these two. Now the real question is which is more important. I think the money, we find in my years of research, I find very clear evidence for funding, because in the attachment material in that 2000 Nature paper, we analyze the work found by NSF, NIH, and all these top founders around the world, including the European founders. And you found that compared to the group paperwork that published on the same journal, same year, so likely the same topic, the funded work is inherently and inevitably less disruptive. So I think even after controlling team size, which the communication cost is equal, you still see that strong funding effect. So this, I think, this brings back to we need alternative funding systems.
I think we have time for one or even perhaps two more questions.
I have a question online. Luca asked, and I'll paraphrase. what will you say your findings imply for industry?
Very interesting. So by that question, I think that relates to, bring us to the question by the gentleman earlier about some fields and some activities are determined to have large teams. Like in industry, if you want to make a plant boring, you have to have large teams. Well, I think all I can say based on the data and observation is autonomy and creativity does matter. And I think industry is actually at a better place perhaps than in science in doing innovation nowadays. Why? Because the money works in a very different way there, as based on my very limited knowledge. Because I'm less familiar with the UK system, but for the US system, all the money goes from distributed by these federal agencies, NSF, NIH. And because they are federal agencies, these are tax money. So they need to be highly conservative. They need to justify. And then nowadays, people even look at the published funding reports to see what this money where this money actually go. So these are tax money. These are federal agency behavior. So that they, by its nature, we cannot have venture capitals there. People wish we can have venture capital in science and people will invest in you when you are like 20. But it doesn't work in that way because that's, again, tax money, right? And if you are the taxpayer, you'll be very concerned when they throw big bills to young people and with crazy ideas. But venture capital has been working well in industry, in Silicon Valley. Usually they actually want ideas that may or may not work, because for 100 idea they found, they want that kind of idea that if it works, it will compensate the cost of the other 99 ideas. So they are determined to find the most risky ideas. So long story short, I think there's a huge opportunity in the R&D department in industry in the conversation of how we can extend that venture capital idea, not just for existing established like patterns and technology that like very, very close to profitable and market, but one step back, further to science. And with the rise of these AI companies, they are getting more richer and with more capability to invest in innovation, I see hope.
Two institutions that are probably less prominent in industry, peer review,
yes.
role of gatekeepers,
yes.
such as editors. Is that, do you think, is that having a material impact on the type of science we do?
Yes,
or?
yes. So there was a recent conversation. I attended one of the NBR, which is a US economic workshop on science of science funding. And there are evidence and there are observations from people who leading NIH that peer review is the way to, maybe an efficient way to exclude bad science. But it's not the best way to do most creative good science. So the nature of peer review is if something terrible bad comes to the table, for example, a paper or a proposal, totally bad, doesn't even have a reference or just apparently don't know what they're talking about, it's very efficient to exclude that. So it's like the bottom line of science. But there's no evidence peer review will select the best candidate in job search, best paper in submission, and best proposal in funding. And this observation comes from the leadership of NIH, that they observe that occasionally they need to be a little bit creative beyond the peer review system and found the project, the big control experiments that these leaders, which themselves are also doctors, see potential. And these kind of project, after a few years, in many cases works well. So it paid off. So I think that supports your hypothesis of peer review as the conservative system in science, which again, because industry doesn't have that, so let's hope.
Going by the clock on the table rather than the one that I have on, I think we still have time for another question over there.
Hi, I'm Vedika and I am pursuing a PG diploma in AI for business at Side Business School. Thanks for the presentation. I really like all your points. I just had this one question, which I think already got covered in one of the previous questions, but if you can offer another perspective. So now in the age of AI, we are actually in the dilemma if a lot of teams are just unconsciously getting wiped off from the economy. So why do you think this topic was still relevant today? And shouldn't we be discussing about retaining teams more? So,
The impact of AI on teams, or
sorry.
can you be a
Not
little bit
sure.
specific?
So we were talking about how how there is this additional cost of having additional teams in innovations or within organizations. So why do you think this topic was actually relevant even today? Shouldn't it have been the other way around, where we are talking more about what is the significance of teams, maybe?
You want a more counterbalance about benefits?
So is the question more that with AI you have a additional research assistant and you don't need a team any longer, or I'm not sure if I follow that.
Yeah, so basically, the teams are like people are anyway downsizing within organizations. So why did you feel the need to research on the cost incurred in having teams in the first place?
So what brought you to investigating the topics of teams?
Wow, that's now I'm at a career stage that I can share my personal story. I appreciate that, but I think it's more about the intellectual paradox that attracts me and my coworkers here. That when everyone is celebrating teams, there's like hidden costs going on here, and perhaps if there's a personal touch, that's a touch of myself as an artist. It'll be I'm a social scientist, but now I work in the computer science school, so I miss my times.
And related to that, I think one thing that came out in one of the figures, it seems that team size and disruption for engineering in computer science, it behaves a bit differently. Is that correct? Can you speak to that briefly?
Yeah. So this is like something beyond the paper, but it's true. There are actually two ways to disrupt. So we see that for computer science and engineering, and we also see that for founding works. So in some cases, I'm still feel puzzled about that and try to reconcile that with my majority of findings, that you do see some cases where you need a certain amount of money to even be disruptive. I cannot explain that because the only antidote I can find in the real world is OpenAI. Like if you and the recent news, the DeepSeek in China, right? It's like in certain kind of games, maybe nowadays in AI frontier, you need a ticket, and that ticket to get to play the game of innovation, and that ticket is usually a huge bill and a startup of not so small teams.
So it's a question that you need a lot of compute, you need a lot of maybe different data sources, and you need more people to get those complementary assets.
Yes, my only explanation is that even in fields like that, we talk about delivery, we talk about Turing invent the theory of computing and people who make it true. But I think even in the way of how do you actually make a computer, or how do you actually implement the neural network in the subdomain like that, you still have disruptive innovations, and to do that you need teams and money.
So in the spirit of ending a minute early rather than 10 minutes too late, please do join me in thanking Lingfei Wu for an excellent presentation.
Thank you, everyone.